Okay, in this video I wanted to give some intuition about the disk method for finding volume of a solid of revolution. So first let's start off with what is a solid of revolution, and I think the best way to explain it is just to show you what a solid of revolution is. So I'm going to take this curve, f of x, it's the square root of x, but that's not really important, and I'm going to rotate it around this axis and create a volume, and I'm going to do that in this way. So here's the curve here in the xy plane, and now I'm just going to take a portion of it and I'm going to rotate it around this axis. And this creates this solid here. That's called a solid of revolution because it's created by revolving a curve around an axis. And so our goal is to compute the volume of this solid. And we can find the volume of that solid by noticing this. So if I take this curve of the plane, rotate it here, and I start stacking circles in this way. So each circle will have the radius given by the height of the function. And so I just have to stack up infinitely many of these circles, and I start to get something that looks like my original volume there. So it turns out that if I add up all of these infinitely many areas of these circles, I end up with the volume of this figure here. So when we add up infinitely many things, we're integrating, so we can integrate the areas of all these little circles to get the volume of the solid of revolution. So let's kind of see what that looks like. Okay, we're going to apply some of this intuition to a problem here. So we want to find the volume of the solid generated by revolving the region bounded by f of x equals root x and the x-axis on the interval 0, 4 around the x-axis. So let's sketch our graph here. So we're talking about the square root of x from 0 to 4, so it looks something like this. And we're going to take that and we're going to revolve it around the x-axis like so. Like so. This is our axis of revolution. Now, this gives us a kind of bowl-like shape. So we have like kind of a 3D bowl. And we want to find the volume of this. So in the example that I showed you on the graphing calculator, we took disks around this region here. So we have these disks inside here. And each of these disks has a radius that will allow us to compute its area. So this would be the radius of this disk here. And notice that it's just the height, f of x. So this r equals f of x. So in general, if we want to find the volume of a solid of revolution, we take the integral over the region, in this case from a to b, of pi times our radius squared d whatever our variable is. In this case, it's x because we're integrating horizontally. So in this case, we have the integral from 0 to 4 of pi. Remember, we just said that my radius is f of x, and f of x is the square root of x. So I have pi the square root of x squared dx. Well, that just simplifies to this, 0 to 4 of pi x dx. Integrating this is pi times 1/2 x squared, evaluated from 0 to 4. And then this is going to be pi times 1/2 of 16, which is 8 pi. So the volume of the solid of revolution that I demonstrated in the beginning of the video is 8 pi. Okay, moving on. We want to find the volume of the solid generated by revolving the region bounded by f of x equals x cubed and the x-axis on the interval 0, 2 around the y-axis. Okay, so we have, let me draw our curve here. We have f of x equals x cubed, so that's something like this. And we want to take the region bounded by that and the x-axis. So on the interval 0, 2, so this is 0, let's say this is 2. So this is the region here, and we want to revolve it around the y-axis. So we're taking this and we're revolving around the y-axis. And so that's going to give us this kind of bowl-like figure again. And remember that when we want to find the volume, we need, like we showed before, the integral from a to b of pi r squared. And in this case, we're going to be integrating with respect to y. Why is that? Because our disks here are horizontal. They're perpendicular to the y-axis, so we integrate with respect to y. Now all we need to do is figure out what our radius is and our bounds. So our radius is going to be this x distance here. Because we're integrating with respect to y, I want to solve for my function in terms of y. So we'll write f of x equals to y, and that just means y is equal to x cubed. So this tells me that the cube root of y is equal to x, and this here will be my new function in terms of y. And so my radius here is just that distance from the y-axis to the cube root of y. So my r is actually equal to this. Now for my bounds, I want to find when the cube root of y equals 0, and where the cube root of y equals 2, because remember, those are my x values. These are values in x, so I need to find when these happen in order to figure out what my bounds are. Let me move things over a little bit here. So solving this guy, this just means that y is equal to 0, and then cubing both sides, I get y is equal to 8. So what we're actually after is the integral from 0 to 8 of pi times my radius, which is cube root of y, squared dy. And then, so the cube root of y squared is the same as y to the 3 halves. So I have the integral from, I'll go ahead and move that pi outside. The integral from 0 to 8 of y to the, 2/3 dy. Now integrating, this is going to be pi times 2/3 plus 1 is going to be 5/3, so it's 3 over 5, y to the 5/3, evaluated from 0 to 8. If I evaluate this at 0, then it's going to be 0, so I only have to worry about 8, so this is going to be pi times 3/5 times 8 to the 5/3, and that's going to be pi times 3/5 times 2, because the cube root of 8 is 2, to the 5th. Now this is going to be pi times 3 over 5 times, so this is going to be 32. So my final volume here of this bowl-looking thing is going to be 32 times 3, which is going to be 96 over 5 pi. There we go. Okay, so up until this point, we've been working with the axes, using the x and y axis as our axis of revolution. But in this case, we're talking about just some line in the plane. So we want to find the volume of the solid generated by revolving the region bounded by f of x equals sine x, and the line y equals -1 on the interval 0 pi around the line y equals -1. Okay, so let's take a look here. So just a reminder, our formula that we're given for volume is v equals the integral from a to b over our region of pi r squared, and then we have a d something. So we got to figure out what that is, what variable we're going to be integrating with respect to. So let's go ahead and draw our picture. So f of x equals sine x will look like this. And we're talking about the interval from 0 to pi, so that's just this guy here. And then the line y equals -1. Y equals -1, let me draw it in blue here, is this line here. So we're talking about revolving this region here. This region here around the line y equals -1. So that's going to look something like this. So I'll get these two here, and then it'll have like that. So we're talking about it's kind of like a donut, but with no hole. We have our disks perpendicular to the x-axis. So we notice that our disks are perpendicular to the x-axis. So this tells me that this is going to be my radius here. And so I need to integrate with respect to x. And thinking about my radius. So my radius it's the distance from the x-axis to sine, so that's sine of x, plus the distance from the line y equals -1 to the x-axis, which happens to be 1. So my radius is sine x plus 1. Cool. So now I can, I get my bounds for free because we're integrating on the region 0 to pi. So my volume is going to be equal to the integral from 0 to pi of pi times sine x plus 1 squared dx. Cool. So let's do a little bit of simplifying here. So there's not really a nice u substitution I can do here, so I'll just go ahead and FOIL this out. So this is going to be integral. I'll move the pi outside, 0 to pi of sine squared x plus 2 sine x plus 1 dx. Okay, so I can split this up into a bunch of different integrals. This is going to be v equals pi times the integral from 0 to pi of sine squared x dx plus the integral of 2 sine x from 0 to pi dx plus the integral from 0 to pi of dx. And that's just me breaking this sum up into 3 separate integrals. Now for this leftmost one, I note that sine squared x equals 1 minus cosine 2x over 2. So this becomes the integral from 0 to pi of 1/2 minus 1/2 cosine 2x dx. So this then becomes the integral from 0 to pi of 1/2 dx minus the integral from 0 to pi of 1/2 cosine 2x dx. Doing a small u substitution here will get me that this is going to be negative 1/4 sine of 2x evaluated from 0 to pi. This integral of 1/2 here will become 1/2 x evaluated from 0 to pi. And then the integral of 2 sine x dx is going to be negative 2 cosine x evaluated from 0 to pi, and then plus x evaluated from 0 to pi. Okay. Finally, we have that the volume is going to be equal to pi times 1/2 pi minus 0 minus, we'll do plus negative 1/4. So something to notice here. Something to notice here is that at both 0 and pi, sine is 0. So this guy will evaluate to 0, and then minus 2 cosine of pi plus 2 cosine of 0, and then plus pi. Okay, so now I have the volume is equal to pi times 1/2 pi. Cosine of pi is -1, so I have plus 2. And then cosine of 0 is +1, so I have plus 2 plus pi. So this will evaluate to pi times 3/2 pi plus 4, or 3/2 pi squared plus 4 pi. And that would be the volume of this odd-looking three-dimensional shape here. And yeah, that's kind of all I want to say about the disk method. If you found this helpful, please consider liking and subscribing. Thanks. Hello.